All of you welcome in your next period of Maths Paper 1. We start unit number 2, mean value theorems. The first mean value theorem, we say the Rolle's theorem. The statement of the Rolle's theorem: if a real valued function f defined on the closed interval ab is continuous on closed interval ab, differentiable on the open interval ab, and f of a equal to f of b, then there exists at least one point c belongs to open interval ab such that f dash of c equal to 0. We see the proof. First, if f of x equal to 0 for every x belongs to ab, then f become constant function and satisfies. If f of x is constant, then the derivative of f of x is 0 for any x belongs to ab trivially. Satisfies the equation f dash of x equal to 0 for any x belongs to open interval ab trivially. Therefore, we say that the theorem is true, that is f dash of c equal to 0 trivially if the function f of x equal to 0. Then we consider let f of x is not equal to 0, that is let f does not vanish. F does not vanish, that is f is not equal to 0. Now condition 1, that is f of x is continuous on closed interval ab. By this condition, we imply that the function is bounded on the closed interval ab. That is condition 1 implies f is bounded on the closed interval ab. Therefore, let f of t equal to m, which is the lower upper bound of the function, and f of u equal to m equal to glb, greatest lower bound of the function. Now consider two cases. Let m equal to m and let m is not equal to m. First case, let m equal to m, then f is constant function and we have f dash of x equal to 0 for every x. F dash of x equal to 0 for every x belongs to open closed interval ab. Therefore, the theorem is true for this case. Then we consider case number 2. Let m is not equal to m and let m is not equal to f of a. Let f attains m at x, that is f of x is equal to m for x lies between a and b. Therefore, we have f of x plus h minus f of a is less than 0 and f of x minus h minus f of x is less than 0. Since f of x equal to m. Now we are dividing by h and taking the limit h tends to 0 of these both the equations. Therefore, dividing here by h, limit h tends to 0, f of x plus h minus f of h divided by h is less than or equal to 0, and the second limit limit x tends to 0, f of x minus h minus f of h divided by minus h is greater than or equal to 0. Now this ratio and this ratio is strictly less than 0, it is strictly greater than 0. Now here we take the limit, left hand limit, right hand limit, we have less than or equal to 0 and greater than or equal to 0. Therefore, by definition of limit, by definition of derivative, this limit is nothing but derivative. If the limit of this function, if the limit of this ratio exists, then it is called as derivative. Here also the derivative. Therefore, by definition of derivative, this is the right hand derivative, f dash of x plus for right hand derivative, f dash of x plus is less than or equal to 0. Now this is the left hand derivative, that is we write f dash of x minus greater than or equal to 0. Take it as equation number 1. Now by condition 2 of the theorem, what is the condition 2? F of x is differentiable on the open interval ab. F of x is differentiable on open interval ab. Therefore, by definition of differentiability, we have f dash of x plus equal to f dash of x minus equal to f dash of x. That is by definition of the derivative. By differentiability of the function, what is the condition? The right hand derivative equal to the left hand derivative equal to derivative of the function at x. From equation 1 and 2, 1 and 2, the equations 1 and 2 are simultaneously possible only if f dash of x equal to 0 or some x belongs to open interval AB. Hence, we have to show that if f is a relevant function and this condition are satisfied, three conditions: continuous on open closed interval AB, differentiable on open interval AB, and f of a equal to f of b, then there exists at least one point C in between the interval a and b such that f dash of c equal to 0. Therefore, we prove the Rolle's theorem. Here we get f dash of x equal to 0 for some x belongs to open interval AB. This is the proof of the theorem. Then we see the examples on this theorem, that is prove that the functions, given functions are verify the Rolle's theorem for the given functions, or whether the conditions of the Rolle's theorem are satisfied or not, whether the Rolle's theorem is applicable for the function or not. Take the example. Verify the Rolle's theorem for the functions. First, f of x equal to x square plus x minus 6 equal to 0 in the closed interval minus 3 to. Second, f of x equal to mod of x in the interval minus 1 1. Solution. First we see the first example. F of x equal to this, x square plus x minus 6 equal to 0. Now to prove the Rolle's theorem, we have to prove the three conditions are satisfied, and we have to show that there exists at least one point C belongs to open interval AB such that f dash of c equal to 0. That is, C point lies between the interval open interval AB. Here the function is polynomial. Here x square plus x minus 6 equal to 0 is a polynomial function. Therefore, it is always continuous. Therefore, it is continuous on the closed interval minus 3 2. Also, we see that it is differentiable on the open interval minus 3 2. Also, it is differentiable on the open interval minus 3 2. Then we see the third condition of the Rolle's theorem, that is f of a equal to f of b. Here a equal to minus 3 and b equal to 2. Therefore, f of a, that is f of minus 3. What I get f of minus 3 from this? Put here x equal to 3, we get f of minus 3. Therefore, minus 3 square plus minus 3 minus 6 equal to, what do you get? Minus 3 square 9 minus 3 minus 6. Therefore, we have written 9 minus 9, which is 0. Then what you get? F of b. F of b, that is f of 2. Now f of 2 from the equation, from this equation, put here x equal to 2. Therefore 2 square plus 2 minus 6 equal to 4 plus 6, 4 plus 2 minus 6. 6 minus 6 equal to 0. Therefore we obtain that f of minus 3 equal to 0 and f of 2 equal to 0. Therefore both are equal. Hence f of minus 3 equal to f of 2 equal to 0. Therefore we say that the third condition of the Rolle's theorem is verified, satisfied. Therefore all the three conditions of the Rolle's theorem are satisfied. Therefore all the three conditions of the Rolle's theorem are satisfied. Therefore, according to Rolle's theorem, there exists at least one point C belongs to open interval AB such that f dash of x is equal to 0. Hence, by Rolle's theorem, there exists at least one point C belongs to AB. Here C belongs to minus 3, 2, because the interval is closed interval minus 3, 2, open interval we get minus 3, 2, such that f dash of C equal to 0. Now first find f dash of x, differentiating f of x equal to x square plus x minus 6. Therefore f dash of x, derivative of this, derivative of x square twice x plus 1, derivative of 6 is 0. Therefore f dash of C equal to 0, it implies f dash of C means twice C plus 1 equal to 0. Therefore twice C plus 1 equal to 0. Therefore C equal to minus half. Now say whether it belongs to the open interval AB or not. Now open interval is minus 3 to. Now C equal to minus half, which belongs to this interval, because there are the points between on the number line. This is nothing but 3 2 means here minus 3, here minus 2, minus 1 and 0, here is 1, here is 2. Therefore this point C equal to minus half lies between the two numbers minus 3, 2, minus 3 and 2. In between this there is a number minus half. Minus half lies between these two. Here 1. Therefore we say that there exists point C belongs to open interval AB such that f dash of C equal to 0. Hence the Rolle's theorem is verified. Implies there exists at least one point C equal to minus 1 by 2 belongs to open interval minus 3 2 such that f dash of C equal to 0. That is f dash of minus half equal to 0. Hence the Rolle's theorem is verified for the function f of x equal to x1 plus x minus 6 equal to 0. Similarly we take for the function f of x equal to mod of x in the interval minus 1 1. Here the closed interval is this AB. Therefore a equal to minus 1 and b equal to 1. Example 2. F of x equal to mod x in the interval minus 1, 1. A equal to minus 1 and B equal to 1. Here f of x continuous in this interval. Here f of x is continuous in the interval minus 1, 1. Then we check for the differentiability, whether it is differentiable or not differentiable on the open interval minus 3, 2. Let there is a point 0 belongs to the open interval minus 1, 1. Now I show that here this function is not differentiable at the point 0, x equal to 0 in the open interval minus 1, 1. We show that f of x is not differentiable at x equal to 0. Therefore, by definition of differentiability, the condition is not satisfied. We have to show that the left hand derivative is not equal to right hand derivative. First we find the right hand derivative f dash of 0 plus f dash of 0 plus means right hand derivative equal to limit x tends to 0 f of x minus f of 0 divided by x minus 0. Therefore, limit x tends to 0 f of x, the function is defined like this: f of x equal to mod of x. Therefore, f of x we put in value mod of x, f of 0, put here x equal to 0, mod of 0, this y 0 divided by x minus 0, this as it is. Mod of 0 we have 0, and this is the right hand derivative. For right hand derivative we have mod of x equal to x. Therefore, limit x tends to 0, x divided by x equal to, we get 1, since mod of x equal to x for right hand function, for the for the positive values. Then we find the left hand derivative and f dash of 0 minus left hand derivative, that is limit x tends to 0 for the right hand derivative. We write here 0 plus, here 0 plus. For the left hand derivative we write x tends to 0 minus. Therefore, again by definition of derivative we have limit x tends to 0 minus f of x minus f of 0 divided by x minus 0 equal to limit x tends to 0 minus mod of x minus mod of 0 divided by x minus 0. Now x tends to 0 minus means for negative values we have mod of x equal to minus x. Therefore, we write minus x divided by x equal to minus 1. Since mod of x equal to minus x for the negative values. Now from 1 and 2 we observe that these are not equal. Here we get the right hand derivative equal to 1 and the left hand derivative is minus 1. Both are not equal. Hence, my equations 1 and 2, f dash of 0 plus is not equal to f dash of 0 minus. That is, right hand derivative is not equal to left hand derivative. Therefore, the second condition of the Rolle's theorem, that f of x is differentiable on the open interval minus 1 1, is not satisfied. Hence, f of x is not differentiable on the interval minus 1 1 for x equal to 0. That is condition 2 of the Rolle's theorem is not satisfied. That is, condition 2 of the Rolle's theorem is not satisfied. Hence, Rolle's theorem is not applicable for this function. In the interval minus 1 1.